great. Thank you, Tony. Hi, everyone. Welcome to this webinar session being hosted through IRPIC Collaborations, which is a platform that connects federal government researchers, non-federal researchers, and Arctic communities to work together on pressing Arctic research issues. My name is Hailong Wang, co-leading the IRPIC Arctic Systems Interaction Team, along with Renu Joseph, Sean Serbin, Max Stevens, and Joel Wang. The systems team aims to enhance the ability to observe, understand, predict, and project the Arctic's dynamic interconnected systems and their links to the Earth system. Along with several other IRPIC teams and communities of practice, we organize this Arctic Extremes webinar series aiming to explore the characteristics, mechanisms, primary drivers, and predictability of different types of Arctic extremes. Through this series, we will examine the variability and trends, model representation, prediction, and the impacts of various Arctic extremes, as well as their interconnected nature among the Arctic systems. So we are now in this fourth meeting of the Arctic Extremes webinar series. We are fortunate to have two experts in the field on the topic of cold air outbreaks. Without further ado, now I'm turning it to Joel, who will introduce our speakers and their presentations. Thank you.
Thank you. Hello. I'm Joel Wang, a professor at the University of Illinois at Urbana-Champaign. It is my pleasure to introduce our two speakers today. Our first speaker is Dr. Jim Overland. Jim is a research oceanographer at NOAA's Pacific Marine Environmental Laboratory. Jim's research focuses on scientific support for decision makers on climate change and ecosystems in the Arctic and subarctic. Jim has led many projects, including historical climate changes and climate and sea ice projections in northern latitudes. Jim has also served on many leadership positions, including the Arctic Council and the International Arctic Science Committee on Arctic climate change. Jim will talk about cold air outbreaks from the observational perspective. Our second speaker, Dr. Gudrun McNair-Daughter, will talk about cold air outbreaks from a modeling perspective. Gudrun is a chancellor's professor at the University of California, Irvine. Her research focuses on atmospheric and climate dynamics, with specializations in atmosphere, ocean, sea ice interactions, the polar jet, and the ITCZ. Gudrun has served as editor for geophysical research letters and also served on the scientific steering committee of U.S. CLEVA. She is also a member of the Board of Trustees of the University Cooperation for Atmospheric Research, or UCAR, Board of Trustees. Each speaker will give a 15-minute presentation. After the first presentation, we will have time for quick clarification questions, but we ask you to save the substantive questions after the second presentation. Okay, without further ado, I'm turning this over to Jim.
Okay, I like to say hello to many long-term friends that are on the call. Nice to know you're still around. The two main take-homes from cold air outbreaks is there tend to be regional and episodic in scope. So in looking at Arctic mid-latitude connections, a lot of the controversy is people that look at monthly or seasonal averages or large aerial averages tend to average things out, that colder outbreak extremes are really 1 week to 10 days or so, and they often are followed by warm events. So they averaging out. And a report from the National Academy on Extremes just came out today, and they highlight that global warming impact on extremes is to make individual events stronger. So that is true for the Arctic. Next slide. My co-authors are Varunish, Chandra, and Nguyen Wang. A lot of the work here is from our postdoc Varunish, and he'll be available in a year or so, and is outstanding on large data sets. Next slide. I mentioned their regional blocking tends to be in both continents, the Alaska Ridge and Greenland block over North America, and the Ural block and the Okhotsk block over Eastern Asia, and these represent the regions that have downstream influence and upstream influence. The next slide. So we've zeroed in on North America, and cold air outbreaks are really low level events. And so we've looked at the events for January and February over 47 years. And we like the indicator by Huang that looks both at the intensity of the cold air event and its aerial extent. So these are the results from compositing those events. Notice the strong area over the Great Plains area. Next slide. And we often think of cold air events in the U.S. on the East Coast, but this Great Plains area is real major. Here's a major event that went down into Texas with minus 15-degree intensity over several days. So that they're individual strong events. Next slide. And here's the composite 500 millibar for all the cold air outbreak events that show a real strong Alaska ridge and a downstream trough with strong zonal winds. And this is important for the next slide. Next slide. So in looking at cold air outbreaks, you really want to look at the low level cold air advection and minus V del T, and for all these events. We see a major region to the west of the Great Lakes, and something we didn't really expect is because the mid-continent is colder than the East Coast. When you have these strong westerlies in the trough, you have another region of cold air outbreaks along the East Coast. So this was the importance of looking at cold air outbreaks in terms of cold air advection rather than just where the uh, troughs are. Next slide. There's some connection with the lower stratosphere. For North America, you can see that if you have the lower stratosphere polar vortex is displaced over North America, you can have an influence all the way down. And another pattern is the stretch pattern that goes from Asia to North America, and that's more of an Atlantic pattern and East Coast reinforcement. Next slide. So this is a complicated slide, but it's the key to the talk. These are the time evolution of cold air outbreaks, and each picture is the longitude height plot at the given time. So we have lined up with the most intense cold air outbreak. So about 9 days before, we see the development of the Alaska Ridge, and all the heights increase all the way from the surface up to the upper troposphere. And so these are very barotropic features. And so that continues to develop until a few days before the strong event. You have a reinforcement in the lower stratosphere with the dipole of height, ridge, and trough. And a key point here is the stratosphere doesn't really kick in until later. So the barotropic troposphere is the main feature, and the stratosphere reinforces it later on. So people have tried to look for precursors in the stratosphere, and it's actually the reverse, that the barotropic troposphere starts early, and the lower stratosphere reinforces it, and the event dies out by about 5 days after the strongest event. So next slide. So in summary, the cold air outbreaks are regional and episodic. You need to look at the sub-monthly data, and the main features on all of these blocks are the strong barotropic structure that they have. We'll hear more about prediction in the next talk, but from what we've seen so far, these cold air outbreaks and the associated blocking are intrinsic atmospheric structures. So you get the start of an instability, and then the blocks are self-reinforcing, so it's hard to come up with precursors for prediction. So that's what I had.
Thank you, Jim. Do we have any quick questions for Jim? Okay, if we don't have any questions, we will move on with the next presentation by Gudrun. Gudrun, you are muted.
Okay, I'm here, and let's see, I'm looking to share. Okay. Share. Okay. Okay. And okay. Does this look okay?
Yeah, it looks good. Yeah.
Okay, so let me start. Thank you so much for inviting me and for listening to this. I'm going to try to talk about cold air outbreaks in terms of it motivated PMIP with polar amplification MIP. So what have you learned and where are we now? And it's a broad topic and I will probably run out of time, but please remind me if I am. So listed here are the people. We had a project where we ran two models, the Wacom one from NCAR, the high top model, and E3SM. It was a DOE sponsored project and it ended some time ago. And listed are all the participants from that project. It was a great group. And Julian Arnhem is a current graduate student, so he didn't participate in that, but hopefully I'll get to some of his results. So as far as I said before, the PMIP was really in part motivated by cold air outbreaks. And that was because 15 to 20 years ago, there was a vigorous debate about whether sea ice loss was leading to more severe cold air outbreaks over mid-latitude continents. And various workshops were held, as many of you remember, to try to settle this. The problem we faced was that the observational record was too short to isolate the signal from the noise. And when we turned to model results, it turned out that there was just such difference in terms of the sea ice forcing used and different modeling protocols, etc. So it was really hard to reconcile the diversity of results in the literature. So PMIP grew out of this environment and took off at around 2018 or so. And this was an international effort, and around 15 groups participated and ran at least the lowest tier experiments. So this is from a paper by Smith et al., and it's a PMIP synthesis paper. The lowest tier experiments that all the groups ran examined the impact of sea ice forcing or sea ice loss that's shown on the left in this figure. That corresponds to 2 degrees warming over pre-industrial global temperatures. So this was the forcing used, and in the middle panel is the response in terms of surface temperature, and on the right in terms of mean sea level pressure. As you can see, the maximum warming takes place where there is loss of sea ice, and in terms of sea level pressure, the heat low forms over the maximum warming and the high pressure ridge over Greenland stretching across the high latitude North Atlantic. So this is an NAO type response or negative NAO. And also the ridge extends over the Siberian continent, that's the Siberian high. Now, although these features are statistically significant in the multi-model mean, as shown in the stippling here. There is disagreement between the models on the sign of the response in many regions. The gray stars indicate where 90% of the models agree on the sign, and the black stars 100%. So there's, especially in terms of mean sea level pressure, you can see there are regions that are statistically significant, but are not in agreement. This shows, and that's the dynamical part of the response. So here I show each individual model response in terms of zonal mean wind, zonal average of the zonal mean wind. And as you can see, there is robust response in the troposphere with all the models. So there's an equatorward shift of the zonal mean wind, and reduction in wind from about 55 to 65 degrees north, and increase at 30 to 40. Those are the two boxes that are shown here. So they largely agree in the troposphere, but as you can see in the stratosphere, it's a totally different story. And this is the multi-model mean shown here. So that reveals a consistent response, at least in the troposphere. So since we're discussing 16 different models, we're averaging over model differences as well as internal variability. Now, a later result by Ye et al. In 2024, they essentially reran the PMIP sea ice forcing experiments in an atmospheric model again. This is a newer version of the Hadley Center model than was used in PMIP, using PMIP sea ice forcing and very large ensembles, so about 2,000 members. This was to robustly try to quantify the dynamical response. And as you can see on the right, we see the response in terms of surface temperature and sea level pressure below. Very similar to the PMIP multi-model ensemble, except the response is stronger. So there's less internal variability, obviously. And you can see that, yeah, and so what is happening? Well, we can discuss that later. Also, what is interesting, having such large ensemble, is that you can actually tease out much more out of the results. So shown here is the response in daily surface air temperature variability to projected sea ice loss. So you can see there is decrease in variance. It dominates the response over large areas in the high and mid latitudes, especially where sea ice is lost, but much further afield. And well, I'm jumping here. So, and also for the cold extreme, we can look at 5% and 1% of the temperature distribution in daily surface temperature. That's shown here below. And it has shown here on the left-hand side below is the same figure as I showed before in terms of the response in surface air temperature. And you can see this change in the distribution of cold extremes is very similar to the distribution of the mean itself. So that means that the pattern, this is dominated by less severe cold extreme. And note that in North America, well, there was no cooling to begin with in North America, and the dynamical response was really related, in terms of temperature, was really related to the growth of the Siberian high. And we can see in terms of extreme cold. So there are still cold extremes, but they're much warmer, according to this, due to sea ice loss. So sea ice loss in isolation, sea ice loss by itself, only supports more extreme cold extremes over Asia. What about observations or reanalysis? So this is a recent study by Russell Blackport and John Five from 2024, where they look at era 5. So trends for winter, December, January, February, 1980 to 2022 in mean surface air temperature. So these are daily means. and cold extremes. So that's the second percentile of the distribution. So on the left here is the trend in the mean temperature, and as you can see, it's mostly warming over North America, although with the signal is very small in the central part of over a large extent of the continent. But the trend in the coldest part of the distribution is very convincing. It's very warm. So the trend is very positive over the entire continent here, the second percentile. And the difference shows that the second percentile days are warming faster than the mean. This is from ERA 5 reanalysis. Now, they also looked at 7 large ensemble experiments forced by historical forcing over the same period, and get very similar results in that the mean is getting warmer and the second percentile days are warming faster than the mean. This is also from their study, and it compares the trends in reanalysis now averaged over CONUS of the continental US and southern Canada, and compare that to, so that's the black here, reanalysis, and this is the second percentile, trend in second percentile. They also show the 98th percentile, so that would be the warmest, the warm extreme. But you can see that first of all, notice the uncertainty in in the trend. There's large uncertainty here. However, it's above 0. So and also it confirms. So it's within the distribution of all of the model. Distribution of the model trends. We look here. These are the model. Of course, we have many ensemble members here in the model. So there's many more samples to compare to. But so this was a very convincing study. So and of course, when we are dealing with observations or reanalysis, we are thinking about the whole system. We're not just isolating sea ice forcing. And moreover, we're taking into account the ocean. So coupled experiments were actually part of PMIP, but there was no forcing or unified forcing like there was for the atmospheric GCMs. So it was much harder to compare the experiments, but the effect of the ocean is really great. And this is from a paper by Desser et al. From 2015. That was probably the first to point this out. And it shows same sea ice forcing in a coupled model here on the left to an atmospheric GCM on the right. This is the sea ice loss they were forcing with. So there are 2 striking differences. First of all, look at the warming throughout the troposphere. Even if we just look at the northern hemisphere, so look at everything north of here, there is warming throughout the troposphere and the northern hemisphere. But especially it's apparent this forcing this is what we call mini global warming. And this is due to warming sea surface temperatures due to ocean heat transport. So there is large warming just due to warming sea surface temperature in the couple, even though you're only forcing with sea ice forcing. Of course, this is absent in the atmospheric model. And secondly, the Arctic warming extends much deeper in this case in the coupled experiment than in the atmosphere only, much deeper in the troposphere. And that has really important implications for the Siberian high, because that is.
Gudrun, I have 2 more minutes.
Okay, thank you. So, however, the way sea ice loss is forced in coupled models is problematic. So we have, there are other ways to force warming in the Arctic. And I just want to go back to the kind of total picture. We have the upper tropospheric warming as part of the hotspots in climate protection, and sea ice forcing in coupled model leads to a mini global warming or mini UTW. And then we have the Arctic amplification that we're focused on here. But the polar stratospheric warming or cooling, that's really very uncertain. It could be either sign. So one other way to force this Arctic warming is to go directly and force it in a model, and that's what we've done. Julian Arnhem is working on this, and so we go in. This is the result from lens 1 of end of the century, and early century in terms of the jet behavior. Lens 1 that has a very extensive Arctic warming, and lens 2 has weak Arctic warming, but however deep, large UTW. So there's a squeezing of the jet in lens 1, stronger westerlies. Lens 2 has north shifted, still strong westerlies. Remember, that's where the UTW dominates. When we warm the Arctic as much as in lens 1, so we put the Arctic warming in lens 2 to be equivalent to lens 1, we get even more squeezing of the jet because the UTW, there's the mini global warming that even gets it even further. So, so to summarize and some closing thoughts, the PMIP simulations from different models exhibit good agreement overall. Response is weak. Response to sea ice loss is weak. And this was pretty weak forcing compared to some other sea ice forced experiments, with no significant impacts on the mid-latitude climate. Arctic sea ice loss is only one component of Arctic warming. Simulations with imposed Arctic warming, where we actually force the warming in the Arctic directly, exhibit a greater response in the Siberian high, which is linearly scaled with the vertical extent of Arctic warming. In the real world, vertical structure of Arctic warming has a large interannual variability, and Jim came to that, making Arctic mid-latitude teleconnections very intermittent and difficult to detect. And recent study of reanalysis data over 1980 to 2022 demonstrate that cold extremes over North America are getting warmer. That was a result of their study. And that was a nice study by Russell Blackport and John Five. Future PMIP presents opportunity, and I certainly hope there will be future PMIP, present opportunities to explore different ways of forcing Arctic warming other than sea ice loss. And that's important to focus, and it is important to focus on coordinated coupled experiments where we use uniform forcing so we can compare directly modeling results. Thank you.
Thank you. Thank you very much, Gudrun. Yeah, I want to thank both speakers for the excellent talks. Any questions to Gudrun or Jim? If you have any questions, please raise your hand. Maybe I will start with a question. Gudrun, in one of your earlier slides, you showed the vertical cross-section of the zonal wind response to sea ice loss. It seems there are like two general groups of model responses. One is like a maximum response in the stratosphere. The other group is maximum response in the troposphere. Is my impression correct?
The stratospheric response was very uncertain. So some of these ensembles, some of these model results were average only had 100 ensemble members. Others had 300 ensemble members. Even in the 300 ensemble members, we couldn't get robust signal in the stratosphere. So it's just very, very uncertain. And I don't think it's it's just very uncertain what the response in the stratosphere is.
Yeah, I think that's consistent with what Jim showed, before cold air outbreaks, the signals in the stratosphere are relatively weak. But I was also wondering, is that related to different types of cold air outbreaks? Is it possible some CAOs may originate from associated with precursors in the stratosphere, but when we put everything together, the signals are kind of diluted.
It's possible. It's just there's so much variability in the stratosphere. It's very hard to get a handle on it. And rather than being in two groups, it was just they were all over the place, the model results in the stratosphere.
More than two
So
groups.
we saw this, and so we originally the PMIP agreement was to run 100 ensemble members, and we ran 300 because we wanted to get some results of the stratospheric response. After all, we were running a high top model in WACOM, but even 300 was not enough, really.
Hailong, go ahead. Yeah.
Yeah. Thank you for both for the great presentations. My questions maybe for both of you. In Jim's presentation, basically the atmospheric source of predictability of cold air outbreak is in the blocking the circulation patterns in the different blocking patterns. And Gudrun, for the PMIP, we presented different perturbation experiments from sea ice to warming to all those to see the 2-second percentile response. Looks like for the predictability from the atmosphere pattern is pretty short, right? The lead time maybe a week to 10 days. But from the PMIP experiment, could you robustly identify some other sources of predictability from ocean ice or air-sea interactions from those perspectives?
Yeah, I wish I could. No, I can't. But we looked at reanalysis data and because we were very interested in this connection, the deeper the Arctic warming, the more of a Siberian high you built. And that's really the root of the teleconnection over the Asian continent. That's the dynamical response over the Asian continent. And it's just very episodic, and it's very episodic. Some years there's just very large interannual variability in terms of how deep the Arctic warming is, and the teleconnection really seems to depend on that.
Yeah, in terms of cold air outbreak extremes, I pointed out that they're episodic on sub-monthly scales. So the Blackport 3-month averages are averaging all those out. What we found is there's year-to-year variability in the number of cold air outbreaks, but you normally have at least 2 or 3 cold air outbreaks every year. So, and they tend to be intrinsic atmospheric internal variability, and so they've been going on forever. It's not just the Arctic warming time. and and we think it's pretty hard to find precursors because the case studies that we've looked at are you start to have an instability and they feed on themselves, amplifying themselves. So when the initial um, instability happens, there doesn't seem to be uh, strong precursors there, and we started out by a lot of people looking at the stratosphere going down and doing the reverse, looking at cold air outbreaks and looking up. The blocking tends to occur in the troposphere before the stratosphere, so the stratosphere doesn't really seem to be a precursor.
Yes, you're absolutely right, Jim. These are synoptic events over North America. They're not, so it's over Asia that you have this teleconnection that is related to the Arctic. Okay. In North America, it's much more synoptic,
Well,
synoptic.
but we've been working with our Korean colleagues and that stretch vortex happens at East Asia at the same time it's happening over North America. So, East Asia has uh, a large series of cold air outbreaks as well. I agree with you that on longer time scales, what happens over Eurasia is important, and that's why we think we see a lot of these sub-monthly extremes on both on the eastern side of continents rather than in the European center part.
Yeah, I also wanted to mention that so from my perspective, it's if you're looking at teleconnection, it's more to Siberia, to the Arctic. But in North America, sure, there will continue to be cold air outbreaks, but they're getting warmer. They're less severe according to the trend in reanalysis that they show. And they were looking at daily temperatures, by the way. These are daily, not they were not averaging over DJF. They were not averaging over the whole month. They were only working with the winter months, but they were looking at daily distribution of daily temperatures. So, and they find that they are decreasing in intensity. Of course, they will continue to happen because it's synoptic variability, and we will always have weather. That's part of the work.
No, I agree that the intensity may be less, but we've got more people living in the South that have never experienced uh, the cold air outbreak. So even if they're less intense, they may have a larger impact on
Yeah,
people.
that's true.
Thank you for the interesting discussion. Do we have any questions from the audience? Okay, maybe I can ask one more question to both of you, Gudrun and Jim. Gudrun, in your talk, you showed that warm extremes actually warm slower than the mean, but cold extremes is getting warmer at a faster rate. That implies the temperature distribution is getting narrower. Is that mainly related to like the weakened temperature gradient in the lower troposphere? A related question is about what Jim showed in one of his slides. In addition to getting weaker, I think in one of your slides you showed that in the recent decade, cold air outbreaks penetrate less southward. Is that related to the intensity, or it's also related to the circulation change? In other words, the cold air mass is not as cold as in the past, so they do not affect further south or lower latitudes, or the circulation does not push the cold air further south.
I don't want to interpret the results too much because this is not my own work. This is Russell Blackport. But it seems to me that the cold extremes are getting warmer indeed. But the warm extremes are also, this is in winter though. So we're not talking about warming extremes in summer that are definitely getting much warmer. So they only looked at DJF, December, January, February. And that's where the big signal was in terms of the cold extremes getting warmer. And I'm not sure about mechanism. It sounds reasonable what you were talking about. This is synoptic activity, so very much related to weather systems and blocking. Yeah. Does anybody else have opinions on this?
Jim, do you have anything to add?
Yeah, there is some work on the development of blocks, and it seems that there's an interaction of time scales that creates uh, the persistence of those features, but the start, I think, is still pretty intrinsic variability, and but once it starts, then it can hang around for about a week.
Thank you. I see Xiangdong's hand is up. Go ahead, Xiangdong.
Yeah, thank both of you for a great talk. I have two questions. One to Jim, other one to Guru. Okay. Jim, in your study, you have related cold air outbreak to blockings. So actually, in the published studies, there's a mixed signal about the changes of blocking. So do you have any comments if there is changes of frequency of blocking, including both Alaska blocking, Eurasia blocking, and Greenland blocking?
Well, it depends what you think is more important, and
Mhm.
we see a real difference in year-to-year variability in that first time series when we picked out all the cases, and if there's any trend in there, in my mind, they're always swamped by the interannual variability of it, and so I think on several decades you may have that, but I think the large interannual variability, based on year-to-year intrinsic
Okay.
instability is still the main feature.
Okay. That means it's still challenging to link
sea ice declining trend with the changes of cold air outbreaks, right? So because the blocking only show interannual or interdecadal variability.
Yeah, I think, that particularly the Barents Sea and the Ural block,
Mhm.
is really tied together
Mhm.
there. The difference in heat flux from the Chukchi Sea, may have some impact there, but I think the warming in the northern North Pacific with the negative PEO going on is the main determiner of the Alaska Ridge.
Okay. Yeah. Yeah. Thank you. So the second question is to Gurung. Hi, Gurung.
Uh-huh.
And yeah, you gave an excellent summary about the PA MAP research progress. And from your talk, it seems the response to CI is still weak. So if we can, yeah, actually, I recently have many discussions with the colleagues about the Arctic effects and the tropical effects, how they influence the mid-latitudes atmosphere circulation dynamics. Okay, so based on your research and summary, so when we look at what's the progress after Clara workshop and the Aspen workshop, so if we can use one sentence to give a summary, what's a major finding or major progress on that topic
Uh, the effects are
of
robust.
Arctic? Yeah,
Yeah, are robust but weak.
yeah, okay.
And that's
That means the
exactly what,
signal to noise, the
what
signal.
yeah,
Okay.
that's exactly what Doug's paper stated. But moreover, I mean, we understand so much more about the system. I mean, it is a very interactive system, and you cannot just ignore the ocean. You cannot, because there is so much, there's so many feedbacks. And I think for future MIP, it's PA MIP. It's very important to both use different forcing in not only sea ice loss, but also maybe either inject warming into the polar atmosphere or do you CO2 forcing just over an area in the high Arctic, something along those lines. Try different forcings and also coupled experiments and have a standard forcing. So different groups can compare results more directly.
Okay.
Because that was never done for the coupled experiments in PMIP.
Okay. Actually, I have a further question following your suggestions about fully coupled model experiments. You say it should not be limited to CS forcing. So if we use a fully coupled model to do sensitivity experiments, what other forces could be in addition to CIS or in addition to greenhouse gas? So,
Oh, for example, this nudging of temperatures to, to a different Arctic warming, for example, in the atmosphere. That's
okay.
one. That's what I described in the last slide.
Okay. Yeah, I noticed that actually I'm puzzled by a question about that. The warming itself within atmosphere could be consequence, not forcing, not original forcing, right? That could be from feedback process, CS forcing, and the greenhouse gas forcing. So how to isolate that forcing?
Yeah,
Yeah,
that's
that could be really challenging, right?
yes. And
Yeah.
and you can only do that by a series of perturbation experiments.
Okay.
Yeah.
Okay.
If you
Yeah.
can even. I mean, I don't know if it's possible.
Yeah. That's related to the energy budget conservation or balance
Yeah.
question about that. Okay, thank you very much. Mhm.
Yeah, I do realize we are getting to the top of our hour, but I'll make it very quick. Since So it's very impressive that they can run one of the model, the UK model can have a center can run 1,000 members, so ensemble. It's almost impossible for other modeling center given that the models are getting higher and higher resolution. So Guru, do you think AI or any machine learning emulators could help in this regard?
Yeah, I'm sure they can. I mean, we're on the way there. Uh, and by the way, this was Tim Willing's group at Oxford that ran those long experiments, and they used that community platform. And I can't remember the acronym for it, but they use personal computers all over the world.
Oh,
So they were able to run experiments with 2,000 ensemble members, and I don't know the details of it, but they didn't rely on a supercomputing center. They were doing this distributed computing.
oh,
Yeah, and
Another very interesting road is the high resolution experiments and the Arctic refined experiments that we have now, in including E3SM, and also I think NCAR has also a version, although that's atmosphere only. So, but there's a fully coupled Arctic refined version of E3SM. And it would have been interesting if it had been planned more carefully. I mean, in terms of comparing to the regular E3SM, it's very difficult. And Julian is struggling with that right now. But and we're getting different results. So we get much more of a response in the Arctic from the refined model. But and then we get this mini global warming. So we get a feedback in low latitudes that, we didn't have in the coarser modeling experiment. So, but
yeah,
I like your suggestion. I think we're going to rely more and more on AI emulators, at least for
yeah,
some of.
and Hakeem at UOW has looked at some AI models, and they do fairly well on compared to the GCMs on synoptic scales.
Yeah.
So I think there's a lot of potential there to pull out the instabilities over a large range of ensembles.
Yeah, actually, in my group, we've been looking at doing, uh, so we're looking at seasonal prediction of precipitation for California. And we did an experiment with a couple of AI models. They don't beat the E3SMWF model, dynamical model, but they are just as good. And in terms of keeping the coherence of the MJO, they're doing better. This was the NVIDIA huge ensemble. I can't remember the name of the acronym for the model, but it was the NVIDIA model with huge ensemble members that Bill Collins has actually developed at Lawrence Livermore. And just the Google AI model, and I can't remember now, neural GCM. So we got a more coherence in the MJO on just subseasonal timescale. So what was it, 6 weeks or so? But so that's as far as you can push it. But so that's a really challenging territory, trying to push predictability beyond, 4 weeks.
And I just like to acknowledge Varunish Chandra again for most, he did most of the work for the talk.
okay. Great. Thank you both. Yeah.
Yeah, I think we have reached the end of the hour. I think we want to thank both speakers again, and also thank everybody for being here, attending the webinar. Tony, do you have anything else to announce?
Well, I just put it in the chat. Like I said at the top, the recording for this meeting will be available later today on both the event page and our YouTube channel. And that YouTube link is public, so if there's anybody that you know, even if they're not an IARPIC member, you can share the link with them and they can catch up on what they missed.
Okay, great. Thank you. Thank you, everybody.
Thank you,
Thank
guys.
you,
Bye.
everyone.
Bye.
Thank you. Bye-bye.